fourth function. Let's see. Okay, so we've got our extended side of this map. This is the same time one space is sometimes two space, and we'll extend side of written that side of configuration as the self will part of the curvature minus it's we as a sigma and then draw up there the phi, and then the gauge fits in. And the cap. That's not. So this and remember this guy was connections in all sections of this plus. This guy was software forms as section of minus, and then finds functions with imaginary functions whose integral is 0. And what we want to we could do this with a proper map. Now including the next proposition. If they put this smooth. So that's once again recall that if I have now say Hilbert traces in English this, as we'll see in a moment in the context of monopoly, but we say this is smooth. But it's as these are infinite dimensional, you have to be careful about exactly what you mean, and for different situations, what you mean by differentiability could be different. But we're going to take the strongest and simplest notion, this differentiable. That's H if there exists a linear operator, a bounded linear operator from in front of 0, such that if I look at the norm of f of h plus theta minus the norm of the h minus linear operator like that eta, it's not, that should be little of the norm of h, which is a zero faster than just the linear. So we're just saying that L is a weak linear approximation with quite a strong set. So that's our definition. And then it's continuously differentiable on some open set if it's differentiable at every point, and then it's differentiable at every point there's a for each h in that open set there's a linear operator, and we want that to vary continuously.
You mean H or L loss?
A, yes. Yeah. They're very similar, and so whatever. Yeah. Yes, right, exactly. So you immediately see why you should do this in the context of Banach spaces when you think about this automotive differential, because each h, and if it's differential on some open set, for every point in some open set, that each h you get this linear operator from denying a map from this open set to bounded linear operators, which is no longer the Hilbert space, but rather a Banach space. So you want that to be differential. Anyway, I mean, if you want to get higher regularity, you find into the dimensional. I'm not going to worry about that. Because actually our math is very simple. It's the nonlinearities are quadratic. So there's not really anything too complicated here. But for as an example that tells you why this is a nice map, we noted that there was this embedding of L1 and L4. Well, that's fine. But this embedding means that there's a map from L1 times L1 to L2, which sends the error functions to the top. This is U map. And it's I call this V, then the differential F in V C in C of this guy is what you think it is. If you go, but you just have to check the function because of this embedding that the document is easy to check hole. That's easy to do. And I'll just leave that. So the nonlinearities here, just are sigma goes to T goes for that, that's covered by that, and then in the Dirac operator, that's linear, so that's okay, and then put the multiplication by the difference, and that's also covered by that situation. So it's a smooth map. That is differentiable, that's no problem. That's linear. Obviously, a linear map is differential. Then it's derivative is itself, and it's zero or something like that. Okay. It's why is it Fredholm? So that's so let's know some value smoothness. What was the Fredholm property come from? Well, let's let's compute the differential of this guy at let's call it alpha and middle P. So the differential of the curvature part, that's a linear, it's just B plus A. The differential of this guy, well, this guy's quadratic, and let's just say it kind of explicitly. Differential is this thing when I'm sleeping. Minus, let's say. Okay, I'll say. The inverse of Clifford multiplication, and then it's a traceless part of this again. So it's just some quadratic thing. And then there's the Dirac equation. The linearization is by linearizing in the p direction, it gives me that. If I'm linearizing the a direction, it gives me that. And then the last term is E star. That should be an alpha. It's just V star alpha. So again. That should be an alpha. Okay. So in particular, at A naught and 0, this differential is B plus B 0, that term B plus alpha. Next term drops out. Phi is 0, so it's EA a little p, and then E star out. So it's a direct sum of two pieces, and it's a direct sum of B plus B star, mapping LP1 sections. It's a direct sum of this thing, and with Dirac operator, you want to take LP1 section. So L2 section. It's minus. These are both elliptic operators, so they're Fredholm. Great. What's the index? Well, we want to compute the real index. The real index of this guy, the kernel is the first Betty number. The co-kernel is just V plus of x because I got rid of the constants. You'd think that the index of this guy would be V1 minus V plus minus V naught, but I got rid of it. And then this term, well, we have to be careful. We want the real index of BA naught. So I do it naught, BA naught. That's twice the complex index, which I told you earlier. So that's 1/4 C1/3 of S minus the signature of S. And these guys, this guy is minus a half the Euler characteristic of x plus the signature of x plus 1, right, minus 1. Plus. I subtracted some one dimension from the cocoa plus 1. And so you add these guys up, you get 1/4 C1 squared of S minus twice the error that this was minus 3 times the signature plus 1. Sorry about the plus 1, but there it is. Okay, this is a beautiful answer. So we'll see why it's a beautiful answer in a minute. Or more minutes than a minute, but anyway. Where did this strange plus 1 come from? I should have stated this better, because remember this is not that anything. So we're assuming, assuming that we're assuming that, let's say, assuming that V1 is 0, so this term doesn't really contribute, but this is U1 equivariant. So if I would like, so it's a proper now Fredholm map. Well, okay, sorry. We've computed some index somewhere. We'd like to say that at any other point it differs from this guy by a compact operator. So the claim is that this difference is a compact operator, and this difference is what? Well, it's you know, Clifford multiplication by mess. Let's see, capital phi and little phi. And then there's Clifford multiplication by sending little phi and alpha to this source thing here. Now, we have to think a tiny bit. Why is this a compact operator? So it's certainly continuous, no problem, because of the multiplication. These guys are in L21. Capital phi is an L21. Sorry, I should have said that. There's also A minus A naught. Or A minus A naught times middle phi term in here as well for the difference. But again, everything on this side is an L21, but I made a big deal of the fact that L21 and the L2 is not compact. Not compact. If it were compact, then we'd be all set, because then I would use the compact embedding, it would be a compact operator. But so what I want to see is that for fixed, so if I have, let's say, let's look at this, if we have alpha and capital phi fixed, L21, then I want alpha to Clifford multiplication by alpha acting on phi. I want that to be compact. Why is it compact? What do we know about compact operators? Nothing. I said the compact operators were the what of something. Closure. So they are. What is the closure of a set? Closed. You're right. So if I can approximate phi by something better, then this is a compact operator. And I can just, by density of smooth functions, I can approximate this by a smooth phi, where this is a compact operator, and then this resulting limit operator is in the closure. So it is compact by closeness of compact ops. Okay, so really it's okay. I mean, anyway. Somehow I'm trying to protect you from doing too much PDE. Okay, so you should appreciate that. Right? And I'm doing it by using a tiny bit of very basic functional analysis. Okay, so you can thank me later. Right? I'll take it. But otherwise you have to work with subless spaces of higher regularity. Everything would have been much more messy. But it's all good. Okay, great. So it is a Fredholm operator, smooth Fredholm math, I should say. Its index is this magic number. Now what we want to do is, so let's make some, now we can make some definitions. What you might call space. So moduli space each depends on, first of all, on S, but also on the metric, and eta is the extended Seiberg-Witten equations inverse of eta 0, 0, and then divided by U1. And then, yeah, and I might abbreviate this, probably you do well if this is M of S, but anyway. Then inside here, these are equivalent classes. I want to remove the fixed set of the action, and I know what the fixed set is where phi is equal to 0, so that it points in here, so that phi is not equal to 0. Okay, so that's and so here's a line that I'm not going to prove that you can. It's sort of not too hard to do as far as it goes, but let's write any of us or with configurations of A and C that what do we want? We want these guys of solutions to the Dirac equation, and he's not able to do it. Okay, so this is some subset of our configuration space. And the lemma is that this is a smooth. Let's say this one. This guy restricted to points in here is subjective. Which implies by the implicit function theorem and the dimensions that this is a use over manifolds. Okay, and that takes a little bit of work, but we just need to see that the just compute the differential, computed the differential. No, the differential was here. Okay. Anyway, there it was. You can check with some work that it's actually subjective. And this is a fluid manifold. But that's really nice because what the situation I've got is that this now has a projection just to solve the two forms. And I've asked this. I want to be gauge fixed. So still subjective, and so I've gotten rid of two of the equations. I just have the curve equation left, and this is also a Fredholm map of the same index. Well, now we're in an excellent situation if we're studying this guy. Why? Because two nice things have happened. This thing is smooth, and I've arranged the reactions free. Fredholm map, and we want X 3 of them. Okay, and our yeah, so so um, there's another wonderful theorem of infinite dimensional differential topology, Snail's Seiberg-Witten Invariants. So the if we have a smooth Fredholm map, then the set of critical values is meager. So, in other words, these are infinite dimensional manifolds. It doesn't make sense to say the set of critical values can be zero anymore. But what we can say is that it's still a very thin set. It's important in Snail's theorem that you have quite a bit of regularity because I mean, the regularity depends on the index, but the Sarg's theorem, you need to have enough regularity in order to be true. And there's a beautiful example of Whitley of Whitley's staircase of C1 function on the square that has fractal arc critical points. So it's the critical values of everything. So that means that for open dense set eta, my inverse of eta is a smooth manifold of dimension equal to this. Actually, let's do this. We're going to call this E of S plus 1. Dimension E of S plus 1, and it has a free S1 action. So this is our modular space for S. Leads into A dot, and there's a smooth manifold. So we don't have a dimension equal to just the events. Like what okay. Now, so let's say about this a little more, and then we'll start to investigate what we can do with this. So, okay, there's one tiny issue, which is the fixed set. When we get to the fixed set, so So we've got problem when does so i.e. given this line bundle over the form manifold, when is there a anti-self-wall connection? On L. So if that equal to 0, then the curvature of that is equal to F minus. That's what it's called, anti-self-wall. Right? And well, that's an interesting question. So note that so I over 2 pi F A that is a Dirac representative of C1 of L and any Dirac representative arises as I over 2 pi F A prime for some A prime. Why? Because if A prime is A plus little a, then F A prime is F plus DA. So if I don't like the one I have, I can just change it by adding an A. All right, great. Now something interesting happens. So so now we go back to what we learned about self-dual and anti-self-dual forms. So we'd like to solve given A, we want, if there's a representative, we want to find little a so that F plus A plus A plus a little a is 0. And this is a kind of Fredholm alternative situation. What we're asking, therefore, the question is F a plus in the image of B plus. Right? And how do we test that? Well, that's only if and only if for every G self-dual harmonic form, F plus inner product omega is 0. Right? That's linear algebra. But this condition is quite interesting. What does it say if I think about it from what we've learned? Well, this inner product is the integral over x of F plus anyone the I or 2 pi so omega is a real form or whatever. But anyway, it's notice that's this guy, right? Actually, let's just think. It's a Hermitian in the product, but this guy's real, so I don't have to conjugate it, and it's just like that. Okay, so that makes sense. There's an interesting move I can do to this guy, right? Which is, remember, self-dual and anti-self-dual forms are pointwise orthogonal. So this is also equal to FA wedge wedge omega plus. But now this thing could look like a kind of metric geometry problem became a topological problem. This is the cutoff. Right. So this says that well, let's say it more prettily, this is up to the 2 pi I, a Dirac representative of C1, and then the cohomology class, this is a formative cohomology class, this guy is equal to 0. Right. So that's something interesting. And now all of a sudden you start to see where in unrushed functions as long as b plus greater than 0 or greater than 1 comes in. Right? Where this is where it comes in. So you notice that if b plus is 0, and it implies this is 0, it's always solvable. If b plus is positive, then there's an obstruction to solving it. This has to be true for all. And so there's a really interesting piece of geometry happening here. In fact, conformal geometry, because remember the space of self-flow harmonic forms is it is a conformal invariant of the manifold. What do I say? So to summarize what we just proved, proposition L over X and this and it's the connection. Again, this is just a C bundle, emission C bundle. If and only if for all omega in the self-flow harmonic forms, the top product of C1 events with omega plus evaluated on the fundamental class is 0. Okay, so this is, in other words, B plus equations on this first term class. So let's think about the case of B plus of X is equal to 1. Then this is the two-dimensional cohomology, real cohomology, Dirac cohomology. So that is what it is. It is dimension B2, but inside here, there is a line that's the self-flow harmonic forms for a given metric G. And you notice that, remember, B plus is 1, so the quadratic form has one positive eigenvalue, B plus minus 1 negative eigenvalue. So that's why I've drawn this cone. That's the 0 set of the quadratic form. And this line lies inside the positive cone, right? But it moves. It depends on the metric. So you should think of this just like the story for Riemann surfaces, right? The holomorphic forms depend on the conformal structure, while the cohomology itself is, the full cohomology, H1 with C coefficients doesn't, but the 0, 1 part does, and this is a higher dimensional conformal analog of that. So there's something really interesting in four-dimensional conformal geometry and understanding how these subspaces can move. And more generally, we can think of H plus as a subspace of the Gross-Nonian of B plus dimensional subspaces of the cohomology, and it moves around as G moves around. There's some interesting Grassmannian. It's also in this has still has a quadratic form. It's a positive subspace, so there's some generalization of that picture. Okay, so but here's enough place where it's nice to have this generalization. It's nice to have that generalization there with the eta, because here I was asking when it admitted a self-full harmonic form. If I add the eta, then I should put a plus eta there, and then the obstruction changes. It depends on the the harmonic part of eta, and so I can always guarantee that using eta that as long as if B plus is positive, then eta allows me to assume no solutions that M S G eta is equal with has no solutions with spinner is 0. But now I worry. Now I can, so the picture. Here's the picture so far. So here's where eta lives, and then I'm not going to draw it as non-linear, but here's this d of s, and but d of s removed the guys with phi equals 0. There's a circle action that has this phi equals 0 thing as a fixed set, and I can assume that my moduli space for if p plus is bigger than 1, my moduli space is some well, let's say, as it often will be, it's just a union of circles, or maybe if it's higher dimensional, it's a union of S1 invariant submanifolds that are away from here. But now, if we vary beta, then now we can run into trouble. If b plus of x is bigger than 1, we're in good shape. I can find here's my given eta, and as I vary with an eta prime, I have to worry in this one parameter family, is there a solution where phi equals 0? If b plus equals 1, that can happen. There's so back in this picture, if I look at the projected version of this picture, I have just a point that, and then the issue is inside here. That's where C1 is it is cups with these potential guys to be 0. Right, so everything inside the projectization of this is a potential self-dual harmonic form, and this green locus it's one equation. Given C1, this is one equation on this locus. And that my problem when B plus is equal to 1 is that I might pick one of my betas might end up over here, one of them might end up over here, and as I go between them, there can be a bifurcation. But if B plus is bigger than 1, that bifurcation for one parameter families won't happen. And just to tie all this together a little more. But it's
Sorry, before we erase that, I was a bit confused. So,
well,
so here, if like if the derivative of Seiberg-Witten is rejected, don't you also get the derivative of?
sorry. What do you mean?
Oh, you mean derivative of Seiberg-Witten is rejected, or?
But restricted to this, it's sorry. Sorry. Yeah, I see. Imposes the projection to S with section of S minus and yeah, sorry. I mean, I should perhaps I should have said it better. It's trick. The Seiberg-Witten map is going to be very is that linear subspace. That's yeah. Anyway. Okay, so taking stock of where we are at the moment, let's make one more observation. If I define C1 star in set of a P in my configuration space where P is not equal to 0, this has a free S1 action. This is the complement of an infinite dimension linear space. So it's a point for all intents and purposes if you are a homotopy theorist. And therefore, the quotient space is BS1 and it contains our modular space. And so at first pass, the Seiberg-Witten invariant which is defined when B plus of X is bigger than 1, is the fundamental class of this guy in the homology of BS1. So in particular, so I should say at first pass, maybe I mean Z2 homology. I haven't explained how it's oriented, orientable, and how oriented. But what was that? Yeah, of course, we did all this work to prove it's proper. Sorry, we didn't know. So this is compact. What is it? This is a compact manifold. So it has at least a Z2 fundamental class. In fact, anyway, I'm not fixing more things like this. This is orientable and is oriented by an orientation of at the moment, if B1 is 0, it's oriented by an orientation of 3 plus. of X. Basically. That makes sense, you know, if it's orientable, so the idea of orienting it. So let me say a couple of things about that. So the idea for orienting it is that if I look at this linearized extended Seiberg-Witten map, well, this is Fredholm. And so I get a map from a fees to Fredholm operators, from H1 to H0. And as I said, that's a copy of the classifying space of BO. And so, so the orientability issue is boils down to the question of whether the fallback of the H1 class in here by this map is non-trivial. But I just told you that the algebraic modulus space of BS1 has no H1. So it's got to be orientable. And the point is that once you orient, once this family is orientable, that implies that the modulus space is orientable, because along the modulus space, the index bundle is the tangent bundle. Right. So this the index bundle of a feed index is a bundle over this configuration space, this formal K theory element in here that is only restricted to the moduli space when the moduli space is smooth. G theta of the tangent bundle. That's the bundle of kernels. It's the pressure subjective. It's the bundle of kernels that are restricted to that. So that's why it's orientable. And to orient it, I just need to orient it at one point. And then I can orient it when A and phi are when phi is 0. And I notice that the operator decomposed. And it decomposed into a complex operator, which is the Dirac operator. So that part's orientable. And to the subpool operator, whose kernel was trivial, B1 is 0, and co-kernel is H plus. So I just need to orient H plus. So the final upshot, the fundamental class is an element of either 0 or Z. So I can tidily say, that explains what Andras was saying before. This Seiberg-Witten map for a manifold with phi1 equals to 0, we're going to have here from spin C structures to the integers. It's 0 if D of S is not even. Such that maybe this rings a theorem. So invariant is resulting hat. I'll tell you on spin C structures on X, if the integers S value of S is equal to 0 if D and C is odd, and it's equal to whatever C1 plus hyperplane bundle to the D over two evaluated on the model space. Of X. And eta, if not, and that's D over S over two, and you know, what's that? Orientation base plus. And this one's well defined. If B plus X bigger than one. And that's all from yes. Exactly. X is the K3 surface. And I'm going to give it with sorry, but that's a metric, whereas the scalar curvature of the metric is 0. So that implies from the energy identity that if I look at extended Seiberg-Witten that inverse of 0, 0, 0, only solution is 0. Okay, but this manifold is B plus bigger than 1. B plus is 3. And the little trick, which I'll explain better next time. The trick is that if I look at SW inverse of the Calabi metric has a trio of parallel Kähler forms. This guy, it turns out that by staring at the energy identity more carefully, we'll do next time, this guy has this unique solution. There's kind of a canonical A and a parallel phi. Unique solution with unique solution, and it's unique up to up to rotation. So with modular space for the Calabi-metric, that's the CY for any Calabi-metric, and eta being one of the distinguished self-harmonic forms is a point SW of sorry, what spin structure? Spin C structure. K3 is spin, and it's for the spin structure. All this is for the spin structure. So I should say this, we want C of S to be 0. So S is a spin structure. So that means C1 squared bit is 0. By the way, yeah, remember C1 squared minus 2 pi plus 3 sigma over 4, that's the dimension. C1 is 0. Other characteristic of K3 is 24. Signature is minus 16. That's 0, 2. This lattice space is a point, and there's so the Seiberg-Witten invariant of the spin structure for K3 is more. I should decide whether it's plus or minus one, but fixing an orientation of H plus, it's either plus one or minus one. That's really interesting because this is a diffeomorphism invariant. And because it's a diffeomorphism invariant, you know that there is no diffeomorphism that can change the orientation of H plus. So the automorphism group of the intersection form of K3 is, the intersection form of K3 with these two E8 plus 3 hyperbolics. It has the integer automorphisms of this lattice is a huge group, but there's an interesting question of whether there are automorphisms. There's certainly automorphisms of this lattice that change the orientation of H plus. H plus lives in the hyperbolics, right? And if I permute two of the hyperbolics, that's an automorphism that changes the sign of B plus. There's one B plus in each of one element of B plus in each of them, and if I switch them, it changes the orientation. So there's no diffeomorphism of K3 that achieves that automorphism. So we're already learning, from just being able to do one computation, you learn something that is very hard to prove. I mean, you can't prove it sort of otherwise. You prove it Donaldson's merits as well.
Is that something that's always the case if you have a non-trivial Seiberg-Witten invariant?
Yeah, if you have an untrivial Seiberg-Witten invariant, then there's no diffeomorphism that changes the sign of H plus. Yeah, so that's a general fact, and already, not at all a trivial fact. Okay, I think I'm overdone. Yes, overdone.